Today we are going to learn about section 4, which is a confidence interval. Confidence interval is a start of something called inferential statistics, which is you're inferring about the population using your data. You might have heard of this word, margin of error, and in a simple definition, you found margin of error by adding and subtracting 1 over square root of n to your mean. That's how you found the error. So because it's a random sample, that means there's always a little bit of chance variation. Depends on what kind of sample you chose. You can calculate what are the chances of certain variation. So that's what margin of error is. It's kind of like giving you a little bit of like a wiggle room instead of saying the mean has to be 100, and if it's not 100, then it's all failure. So if you think of it in terms of business perspective, yes, you do want to be confident enough that you don't have all this faulty items, but you don't want to get rid of items that are not perfect, but it doesn't create a faultiness. And so think of it as it's a little bit of cushion. So as long as it's in this interval, then you can claim that your product or whatever it is that you're claiming to be okay. Okay, so that's the idea of a confidence interval. So it gives you an estimate. So the mean that we've been using, the sample mean, is something called point estimate because it's a single point that estimates your parameter, right? Your population mean. And confidence interval is an interval estimate because it gives you an interval of an estimation of your parameter. All right, so confidence interval, sometimes they just denote as a CI. How to find it is we don't do it this way. This is, as I said, it's an elementary way. We actually do it a little bit more formal with the equation, which is written right here. Okay, so let's go over what these symbols mean. So X bar is your mean. And Z, this one, is not a z-score, even though there is a relation. We actually call it a critical z-value. And this guy, now you know, it's a sigma, so it's standard deviation for the population, and the n is a sample size. So like I said, z here is not a z-score, even though it kind of is, okay? So when we write z, we actually write z and a little star to say that this is different from a just plain old z-score. So the z-star is a critical value, and the reason it has a relation to the z-score is because of this. Confidence interval is basically saying this. I have a mean right here, and I'm giving myself 90% confidence, meaning that the true mean is between the interval of this point and that point. And that the phrase that I'm 90% confident comes from that probability. Okay? 95% confident, then obviously we'll have a greater z-value because, as you can see, you're getting more confident because you're covering more values. So you can think of it this way. As you get more confident, what you're saying, the interval may be less useful in some sense. Because think about it, if I say that I'm 100% positive that tomorrow the temperature will be between -40 to 40. Yeah, I'm 100% right because, I'm basically covering anything that can happen in the temperature, right, in a spring day. But is it useful? No, not really, because you have no idea, because you would dress very differently for -40 to 40 degrees, right? So confidence level is important because you want to be confident about what you have, but you also don't want to risk losing some of the precision, right? And so if the confidence interval isn't stated, usually they go for the 95% confidence level because it's a compromise of like enough being confident and also giving enough information so that it's still useful. All right. One thing that is important about the confidence interval using the z-critical value is that you're assuming that your distribution is normal, because z-score is only used for the normal distribution, meaning that you have to have a sample size greater than or equal to 30 for central limit theorem to work, and that you can assume normality for the sampling distribution, or that your population sigma is known. Okay, so population standard deviation is known, or that your sample size is large enough that you can use you can assume normal distribution. All right, so what does it look like in our actual problem? Oh, by the way, these z-scores actually do not change. So as long as you have a 90% confidence level, you will always use 1.645. And same thing for 95% and 99%. So let's try number 1. It says the number of days with temperature above freezing for a sample of 35, so n is 35, had a mean of, so we can assume normal, right? Because the central limit theorem. And then, so we are assuming normal due to central limit theorem, and standard deviation is 54.2, and then mean is 190.7. And it says construct a 95% confidence interval. Okay, so then confidence interval basically is mean plus minus z star for 95%, the z star is 1.96. So 1.96 times your standard deviation over square root of n. So this is your z star. So the margin of error, sometimes I write it ME, is the after plus minus part. So that value happens to be 17.96 when I calculate it. So then to find the actual interval is that you add that value to your mean, or you and you have to subtract that value from your interval. Like this. So what does that mean? It means that we are 95% confident that the true mean number of days with temperatures above freezing is between 172.74 days and 208.66 days. Okay, so I'm saying it's one of those points, okay, 95% with confidence level. All right, number 2, find a 90% confidence level of the same thing. So the only thing that is going to change in the formula above is 1.645. So 1.96 becomes 1.645. So we do that. So then the margin of error for this one is 15.07. Again, margin of error is after the plus minus sign. And then my interval is from 175.63 to 205.77. So what does that mean? It means that we are 90% confident that the true mean, so the population mean number of days with temperatures above freezing, lies between 175.63 days to 205.77 days. Okay, so that is the confidence interval for normal distribution. But we learned about not so normal distribution, which is t-distribution. So let's find out how the t-distribution works for the confidence interval. So one thing that was unique about t-distribution was that this one usually had a smaller sample size, because if the sample size is big enough, you can assume normal because of the central limit theorem. And when you have an infinite sample size, then the t-distribution acts like the normal distribution. And so the other concept that came with t-distribution is the degrees of freedom, which is n minus 1, right? So it's always important that you state what degrees of freedom is when you're talking about the t-distribution. So oftentimes your standard deviation for the population is unknown. And sample size could be less than 30. So then we use t-distribution, assuming that your sample itself didn't have an outlier or a strong skewness. Okay, you can see from here the distribution, the formula for confidence interval is very similar to the formula from the z-score. So then what we do is, the only thing that is different is this t. And unlike the z critical value, the t critical value or t star varies based on your confidence level, what we call like 90% or 95%, which is a confidence level, and your degrees of freedom. Okay, so this one you do need a calculator or else that you cannot do this problem. Okay, so I mentioned how that z star is very similar to z-score. It's kind of same, right? And so how can we find the t star for a given confidence level and degrees of freedom? Well, we're going to use inverse t. So if you go to second bars, which is the distribution, you have an option of inverse t, inv t, and then you enter. And they ask you for area and degrees of freedom. So let's look at this with the problem number 1. It says that a manufacturing plant, the threads on 10 randomly selected screws have a mean depth of 0.32 inches and standard deviation of 0.03 inch. Find the 95% confidence level, assuming that it was normally. So like the sample size itself is very small, right? It's only 10, but it's basically giving us a green light for using the t-distribution. So n is only 10, so we use t-distribution, and the degrees of freedom will be 10 minus 1, which is 9. And x bar is 0.32, and standard deviation is 0.03. And then the confidence level is 0.95. So for me, it's often easiest to draw the distribution. And then I want 95%, right? And remember, the inverse norm measures the area from the very beginning. So even though this is the point, this would be the t star, right? This is the point. I wouldn't write 0.95 for my area. I actually need to add this area to my 95 to get this point. Okay, so this is a review of how to use an inverse norm, inverse t. So my area is actually 0.975. Oh, sorry. 0.975, and degrees of freedom is 9. So once I have that, it gives me my t value, t star, which is 2.26. Okay, and this is this t. So now I have everything, so I can actually find a confidence interval, which is 0.32 plus minus 2.26 times 0.03 over square root of 10. Okay? So this gives me an interval of 0.299 to 0.3414. Oh, 341. Let's stop there. All right, let's try number 2 and then we'll be done. This one is confidence level of 99%. So let's draw our thingy first. So it's a 99% here, meaning that this would be 0.5% and this would be 0.5%. So I need to add the area. So it's 0.995, right? 0.995 will be my inverse t area. And then it says that n is 16 because it has a 16 room. So then degrees of freedom is 15. So we're going to use the area of 0.995 with the degrees of freedom to find t star. So let's do that. So then my t star is 2.95. And then what I will do is that I will plug it into the formula. 21 plus minus 2.95 times 4.8 over square root of 16. And I'm running out of time, so I won't actually do the calculation, but hopefully this makes sense. The only difference between t and z is that t, you need to use inverse t to find the t star, whereas a z star is given by this But obviously, you can always use the calculator too.